I am Yujun Zhang from Graduate School of Material Science, University of Hyogo. Here I would like to introduce our recent work about magnetic dynamics in oxide thin films. The title of the presentation is Photo-induced antiferromagnetic-ferromagnetic and spin-state transition in a double-perovskite cobalt oxide thin film. The main result shown here is published in the paper in the lower part of the slide. Please check the details therein if you are interested. First, I would like to introduce the background of our research. With the trend of rapid development of intelligent electronic devices and functional information materials, spintronics has become a booming field in modern condensed matter physics. Instead of only utilizing the electron charge, the spin degree of freedom of electrons can be exploited in spintronic devices with low power consumption, fast speed, and high density. A lot of prototype spintronics devices are demonstrated, such as magnetic tunnel junctions and spin field effect transistors, as shown in the left figure. Novel methods to manipulate the electron spin are the key for the development of spintronics. Ultrafast manipulation of spin by light is a promising strategy due to its low power consumption and fast speed. As shown in the right side figure, light is able to manipulate the magnetization of magnetic materials. Studying dynamic behaviors in magnetic thin films is especially meaningful for achieving deeper comprehension of magnetic properties and electronic structure within very small temporal and spatial scales, which is crucial to the realization of high-density spintronic devices. Previous reports of ultrafast magnetic dynamics mainly focus on demagnetization of ferromagnets, which is often characterized by a transient decrease of magnetization. But transient increase of magnetization induced by light excitation was rarely investigated. In this research, we are investigating gadolinium barium cobalt oxide thin film. This material has an antiferromagnetic-ferromagnetic transition at around 250 K and then spin-state transition at around 350 K. We use optical laser to pump the system and investigated its ultrafast dynamics. By taking advantage of the time-resolved soft X-ray scattering techniques, the dynamic behaviors of both antiferromagnetism and ferromagnetism can be detected in a single experimental instrument. X-ray magnetic circular dichroism in reflectivity, XMCDR, can reflect the ferromagnetism, while antiferromagnetism can be characterized by resonant magnetic X-ray diffraction, RMXD. The experimental setup is shown in the left figure. Photo-induced enhancement of XMCDR and decay of the RMXD can be clearly observed in the right figure, indicating a photo-induced antiferromagnetic-ferromagnetic transition. Photoenergy dependence of the transient XMCDR and reflectivity suggests a concomitant photo-induced spin-state transition. Both the electronic state change and the competition between antiferromagnetic and ferromagnetic exchange interactions simultaneously contribute to the observed magnetic dynamics, as schematically shown in the lower part of the slide. To conclude, we have successfully observed the photo-induced ultrafast antiferromagnetic-ferromagnetic transition accompanied with a spin-state transition at octahedral cobalt sites. Our research indicates significant coupling of magnetism and electronic structure in strongly correlated systems, not only in static states but also in transient states and dynamic behaviors. And it is promising to expect the development of new generations of spintronic devices, which can achieve ultra-fast optical manipulation of both magnetism and the electronic structure,